Hello, and welcome to the Microsoft on AWS Modernization Series, Part 3, Serverless and Container Best Practices. This video builds on Part 1 and Part 2 of the Microsoft on AWS Modernization Series, so check those out if you haven't already. Let's get started. In the first video in this series, we covered the benefits of modernizing. We explored how modernizing can reduce operational costs while improving productivity. Modernizing can drive unnecessary cost out of the architecture while improving operational resilience, using best practices in the cloud for failover, high availability, and disaster recovery. Modernizing will also improve business agility, the ability to react quickly to changing market conditions. In the second video in this series, we discussed breaking a monolithic application into microservices. We covered some of the benefits of microservices and how teams can adapt to a microservices architecture. Because a microservices architecture is loosely coupled, we can change one service without making changes to anything else. We'll discuss some service-specific deployments in detail in this video. In order to get the benefits of microservices without having to completely rewrite the entire application all at once, we decided to use the Strangler Fig pattern. The name of this pattern is based on a type of vine that gradually wraps around a tree and eventually replaces that tree with, you could say, a new architecture. So instead of modernizing the entire monolith all at once in a big bang sort of deployment, we'll use the Strangler Fig pattern to incrementally replace the functionality of the monolith with new microservices. Eventually, the new microservices will completely replace the monolith. Further videos in this series cover additional modernization topics. Part 4 covers migrating and modernizing database workloads, going from a single one-size-fits-all relational approach to using a variety of purpose-built database engines optimized for each microservice. Part 5 covers setting up a data lake to drive analytics and insights across all current and future microservices. And Part 6 covers a modernized DevOps workflow that lets us deploy updates to microservices code in a predictable, automated way. So, check those out once you finish this video. In addition to this series, AWS has a variety of content covering optimization of Microsoft workloads. I want to highlight two in particular. First, the Optimization Series Part 1 video covers optimizing infrastructure and licensing costs on AWS, including the AWS Optimization and Licensing Assessment. Microsoft's licensing terms can be complex, and this video covers some of the considerations for optimizing your workloads and estimating costs. Also, Part 4 of the Optimization series covers Amazon FSx, which is a fully managed Windows-compatible network file share. You can set up an elastic network share without having to manage any server infrastructure. As a reminder, in this webinar series, we are centering on a fictional company, Acme Financial Data Services, or AFDS, to demonstrate key modernization practices. The practices we'll cover have been applied to real AWS customers. We are reproducing those practices here and applying them to AFDS. In phase 1 of their cloud journey, AFDS completed a lift and shift to AWS. This has replicated their on-premises infrastructure in the AWS cloud. In phase 2, AFDS performed a number of optimizations on their AWS infrastructure. You can find some examples of these practices in the Windows on AWS Optimization video series. Even though these optimizations did produce some cost savings and performance benefits, AFDS wants to take the next step and modernize their legacy .NET Framework applications. This modernization will transform these legacy applications so they can take full advantage of running in the cloud. Specifically, we're modernizing AFDS's OneVision platform. This is a monolithic platform designed to manage customer accounts, customer invoices, and the associated inventory. To start on this modernization journey, we looked for microservices that were both easy to extract out of the monolith and provided significant business value to run independently. We selected 3 services to extract: account management, invoicing, and inventory. We encapsulated those services into their own .NET Framework projects, and now we want to modernize our deployment of those microservices on AWS. In this video, we'll cover some of the benefits of converting these microservices to .NET Core, and how to move forward with services we can't convert. We'll decide whether to use serverless or containers for each microservice. And for the microservices that we deploy using containers, we'll discuss how to choose an orchestration platform and a compute platform to run those containers on AWS. Let's start with containers. Why would we want to run microservices in containers in the first place? Although you can run microservices on EC2 instances, a microservice architecture is a great fit for running in containers. Typically, in this architecture, each microservice is running in its own container. This has a number of benefits. First, just like each microservice is independent from other microservices, each container is isolated from other containers. Containers manage dependencies and abstract away the underlying platform, which creates a consistent, portable environment from developer machines all the way up to test and production servers. Developers using containers have a lot fewer works on my machine problems. Containers are easy to scale up and down based on the needs of each microservice. If a service receives a sudden spike of traffic, it's fast and easy to launch additional containers to take up the load. Once the traffic spike is over, you can quickly stop the extra containers to free up resources. And that scalability also makes containers reliable. You can achieve fault tolerance by running multiple containers across a cluster of servers. If one of those containers fails for whatever reason, it's fast and easy to launch a replacement. Container orchestration platforms like Amazon Elastic Container Service and Elastic Kubernetes Service automate tasks like relaunching failed containers to minimize downtime. Finally, containers let you make better use of your infrastructure. On AWS, the orchestration services place containers on EC2 instances to achieve both fault tolerance and efficient utilization of the available resources. So containers are a great fit for microservices, but there are some challenges running a .NET Framework application in a container. Whenever feasible, update your microservices to use .NET Core, soon to be called .NET 5, instead of .NET Framework. Updating to .NET Core gives you more flexibility in how you deploy your microservices and typically reduces your costs by running more efficiently. Let's go over 3 major advantages of .NET Core. In 2019, Microsoft announced that the current version of the .NET Framework, version 4.8, would be the final major release. The .NET Framework is still receiving critical security and reliability updates, but it won't receive new features or improvements. All new development is shifting to .NET Core. .NET Core is more modular, flexible, and lightweight than .NET Framework, so it's easy to include only the libraries you need inside each microservice. This results in smaller services that are faster to start and run more efficiently. The .NET Framework is limited to Windows only, but .NET Core is cross-platform. .NET Core microservices run on Windows or Linux. In many cases, running .NET Core on Linux provides better performance at a lower cost. All of these benefits of .NET Core are especially relevant to microservices. One advantage of the Strangler Fig pattern is that you don't have to port your entire codebase all at once. Different microservices can use different languages. That's part of the power of the microservices architecture. So once you've extracted each microservice, you can evaluate whether that particular service is a good candidate to be ported. To help you along this journey, in July 2020, AWS released the Porting Assistant for .NET, which scans .NET Framework assemblies and generates a compatibility assessment. This tool identifies .NET Framework dependencies and APIs that are incompatible with .NET Core and finds known replacements where applicable. This helps reduce the manual effort needed to port your code. When you can update your code to .NET Core, great. Doing that conversion will expand your options in some significant and valuable ways. But we heard from customers that had applications that they weren't able to update. Maybe the application depends on a legacy library that is .NET Framework only. Or maybe the application is using some APIs that are specific to the .NET Framework or to Windows. In these cases, you can use AWS App2 Container, or A2C, to package up these .NET Framework applications into containers, so you can deploy them on a modernized infrastructure even when you can't update the code. A2C is a new command line tool that helps transform existing applications into containers without needing any code changes. A2C discovers applications running on a server, identifies dependencies, and generates artifacts so that you can seamlessly deploy the application as a container on AWS. On the .NET side, A2C supports ASP.NET web applications using .NET Framework 3.5 or later, running in IIS 7.5 and up. A2C packages these applications into Windows containers. We'll cover some deployment scenarios for these Windows containers later in this video. Now, let's shift back to microservices that can be ported to .NET Core. Containers are not the only option for running these microservices on AWS. For microservices that can be ported to .NET Core, consider running them in AWS Lambda. Lambda is serverless. It lets you run code without provisioning or managing any infrastructure. You only pay for the resources used while your code is running. Lambda supports a variety of programming languages and runtimes, including .NET Core, but not .NET Framework. Lambda is a great choice for microservices that can easily be expressed as a single function with few dependencies and use a consistent, predictable amount of CPU and memory. Lambda is also a great choice for microservices that need to run in response to an event. Lambda integrates with a wide variety of other AWS services, so you can respond to events such as an object being uploaded to an Amazon S3 bucket, or a record written to an Amazon DynamoDB table. You can also execute Lambda functions in response to events thrown by your own microservices. On the other hand, microservices are probably not a good fit for Lambda if they include multiple functions working together, or contain operations that take an unpredictable amount of CPU time and/or memory, incorporate many external libraries and dependencies, retain persistent connections to other resources, such as databases or WebSockets, or require reading from or writing to a disk. In these cases, use containers. In the previous videos in this series, we extracted 3 microservices from the monolith. With .NET Core containers, Lambda, and .NET Framework containers packaged by App2 Container, we can now make a plan for how to deploy each of these services on AWS. The account service performs 4 standard CRUD operations. That's create, read, update, and delete. These operations are self-contained and lightweight, and the microservice code can be ported to .NET Core. So this microservice is a good candidate for Lambda. The invoicing microservice can also be ported to .NET Core, using the Porting Assistant for .NET to identify areas to work on. But it uses a variable amount of memory and includes multiple functions. That makes this microservice a good candidate to run in a Linux container. Finally, the inventory microservice has an important dependency on a legacy library that uses the .NET framework. It isn't currently possible to replace or rewrite this legacy library, so the inventory microservice is a good candidate to be packaged into a Windows container using apt2container. Now we have our 3 microservices, and we've identified which ones are good candidates for containers. How can we run those containers on AWS? You can run containers on EC2 instances by installing Docker onto an instance and manually running your containers. This can work if you only have a handful of containers and services, but this manual approach quickly creates operational challenges as you scale. For example, if you have a cluster of instances, you'll need to manage which containers are running on which instances. You'll want to distribute your containers with an eye to availability. Typically, you'd want to deploy a microservice on multiple instances so that if one instance fails, the other can take up the load. You'd want to monitor the status of all of your containers and replace any containers that fail, ideally in an automated way to minimize downtime. You'd want to deploy additional containers for services that are experiencing high load, then stop those containers once the load subsides. And when you deploy a new version of a container, you typically want to make sure that the new containers are up and running before you stop the old containers. You might even want to do a full blue-green deployment, where you keep the old containers running until you switch over to the new version. These operational tasks quickly become very complex if you try and do them manually. Fortunately, there's an automated solution. To perform all of these management operations and more, a typical container deployment includes an orchestrator layer. Sometimes this is called a control plane. The orchestrator is a service that runs separately from the containers themselves and handles container placement, monitoring, scaling, configuration, and deployments. You can even set up a private network among your containers so they can communicate with each other without going over a public network. The containers themselves run on a compute layer, which is managed by the orchestrator. In this diagram, the compute layer is composed of a cluster of 3 EC2 instances. Each instance has 3 containers running on it, placed there by the orchestrator. You can run a container orchestrator, like Kubernetes or Docker Swarm, on EC2. If you do that, you're responsible for setting up and running all of the infrastructure. This can be a significant amount of maintenance and operational work. At AWS, we call this kind of work undifferentiated heavy lifting. These are the complex IT processes that are needed in the normal course of business just to keep the lights on. Undifferentiated heavy lifting doesn't provide you with a competitive advantage. Undifferentiated heavy lifting doesn't provide you with a competitive advantage, doesn't help you meet your business goals, and ultimately doesn't add value to the mission of your company. One of our goals at AWS is to reduce or eliminate undifferentiated heavy lifting for our customers. To do this for containers, AWS offers 2 fully managed container orchestration services, Amazon Elastic Kubernetes Service, or EKS, and Amazon Elastic Container Service, or ECS. Both EKS and ECS provide container orchestration capabilities, helping you deploy, scale, and manage containerized applications. Both of these services are used by many AWS customers for enterprise-scale production workloads. Let's discuss the Elastic Kubernetes Service first. Kubernetes is a leading open-source container orchestration platform. Again, you can run a Kubernetes cluster on your own EC2 instances, but EKS provides a fully managed Kubernetes environment that lets you focus on your containers while AWS runs the Kubernetes control plane. EKS delivers full compatibility with upstream Kubernetes while integrating with AWS services such as Amazon CloudWatch, Amazon EC2 auto-scaling groups, and Amazon Virtual Private Cloud. As an alternative to Kubernetes, Amazon Elastic Container Service, or ECS, is a fully managed container orchestration platform developed by Amazon. ECS is built on technologies developed from many years of experience running highly scalable services. ECS is built on technologies that have been developed over many years of experience running highly scalable services, and is used extensively within Amazon to power services such as Amazon SageMaker, AWS Batch, and the recommendation engine for Amazon.com. ECS natively integrates with AWS services including Amazon Route 53, AWS Secrets Manager, Amazon CloudWatch, Elastic Load Balancing, AWS App Mesh, and more. So how do you choose between EKS and ECS? So how do you choose between EKS and ECS? If you've already chosen Kubernetes as your orchestrator of choice, for example, if you already have a Kubernetes cluster running on premises, consider EKS first. EKS is upstream Kubernetes. It's fully compatible, so Kubernetes clusters that you run anywhere else are easy to pick up and move into EKS. However, Kubernetes has a pretty steep learning curve. So if you're just starting out with containers, or if you aren't committed to one particular orchestrator, consider ECS first. ECS makes it easier to get up and running with containers, and natively integrates with the rest of the AWS platform. That covers the orchestrator layer. Now let's talk about options for the compute layer. In addition to a choice of 2 fully managed orchestrator services, you also have multiple options for how to run your compute layer. As a reminder, this layer provides the actual computing resources, CPU, memory, etc., that actually run your containers. For your compute layer, you can use a cluster of Amazon EC2 instances. If you're running containers on an EC2 cluster, the orchestrator creates an auto-scaling group of EC2 instances and manages the scale-out and scale-in actions of the group. So if one of your containers needs to scale up, but your existing instances have used all of their capacity, the orchestrator will add a new EC2 instance to the cluster. Likewise, if enough containers stop to free up an entire instance, the orchestrator will terminate that instance. This way, you only pay for the compute capacity that you're using. The orchestrator automatically places containers on instances to maximize resource usage. If you're using ECS, all of this EC2 cluster management is automatic and built in. If you're running EKS, you can deploy the Kubernetes Cluster Autoscaler service into your EKS cluster. This integrates with autoscaling groups to provide similar functionality. Alternatively, you can use AWS Fargate, a serverless compute engine for containers. Because Fargate, like Lambda, is serverless, you don't have to provision, configure, or maintain clusters of EC2 instances. You just specify how much CPU and memory each container needs. Because Fargate, like Lambda, is serverless, you don't have to provision, configure, or manage clusters of EC2 instances. You just specify how much CPU and memory each container needs. Fargate allocates those resources when each container starts up and reclaims them when the container stops. Each container running on Fargate has its own isolation boundary, and doesn't share an OS kernel, CPU, or memory with any other container. You can actually mix and match EC2 and Fargate compute in a single EKS or ECS cluster. So you can specify that some containers should run on Fargate and some should run on EC2. Just like we discussed how to decide between EKS and ECS, let's now cover how to choose between EC2 and Fargate. Both EC2 and Fargate are used by many AWS customers for scalable, reliable, production-ready deployments. If your workload has a consistent demand for many CPU cores and many gigabytes of memory, an EC2 cluster may be the most cost-effective option. An EC2 cluster is built based on the cost of the underlying EC2 instances, so you'll want to densely pack your containers onto your instances, or else you'll be paying for capacity you aren't using. An EC2 cluster is also the best option for containers that benefit from a specialized instance type, such as GPU or machine learning instances. To optimize your cost on EC2, consider using spot and/or reserved instances. Reserved instances are a great savings option when you have a consistent workload, and spot instances can provide an even greater discount for containers that can tolerate interruption. The flexibility of EC2 does come with an operational cost. The maintenance and updates of the EC2 instances in the cluster are your responsibility. AWS periodically publishes new machine images with the latest security updates, but even if you use those images, you are still responsible for updating the instances in your cluster to run the latest version. One final note on EC2. As of October 2020, EC2 is the only compute option that supports Windows containers. Windows containers can't run on Linux instances and vice versa. To ensure that containers are placed on the correct operating system, we recommend that you run Windows and Linux containers in separate clusters. On the other hand, if your workload is highly variable, look at Fargate first. With Fargate, you don't need to allocate CPU or memory capacity ahead of time. When you start a container, Fargate allocates the CPU and memory resources that the container needs. This makes Fargate the optimal choice for workloads that have variable or unpredictable resource usage. For example, if a microservice sees a lot of usage during business hours, but very little usage overnight, then deploying that microservice on Fargate will let the service scale down to one tiny container during off hours and scale back up during the day. You'll only pay for the resources used while your containers are running. No more paying for EC2 capacity that might go unused. Batch workloads and periodic tasks, such as cron jobs and occasional jobs from a queue, are other examples of variable resource usage. These workloads are a great fit for Fargate. Even for large workloads, Fargate provides benefits in manageability and overhead. Customers running Fargate don't have to deal with any server updates or maintenance. For example, when the Spectre meltdown vulnerability was discovered, customers running EC2 clusters had to patch and upgrade those instances, but customers running Fargate were protected automatically because AWS engineers patched the underlying infrastructure behind the scenes. Fargate only supports Linux containers, so Windows containers must run on EC2. As I mentioned earlier, converting your microservices to .NET Core expands your deployment options, because .NET Core containers can run on Linux or Windows. .NET Core containers work great on Fargate. As you're considering which compute model to use, keep in mind that you can mix and match EC2 and Fargate within a single cluster. So you can have consistent workloads running on EC2 and batch or unpredictable jobs running on Fargate. Let's revisit our 3 microservices to decide which compute layer to use. The account service is running on Lambda, so all of this infrastructure is handled automatically by AWS. There's no decision to make here. For the invoicing microservice, this service can be ported to .NET Core so it can run on Linux. As we look at the usage logs, the invoicing microservice sees a lot of variability in traffic. It experiences periodic, unpredictable spikes during business hours and low load during the evening. With this usage pattern, it would be difficult to fully utilize EC2 instances, so Fargate is the best choice. Finally, the inventory microservice will need to run on EC2. Because this service is running on the .NET framework, it's limited to Windows. As of October 2020, EC2 is the only compute layer that supports Windows containers. Even if we were able to do a more significant refactoring and update this microservice to use .NET Core, we still might want to use EC2 for compute if the service has a consistent, predictable load pattern. Now we can see how the extracted microservices will work with the remaining code in the monolith. Remember, because we're using the Strangler Fig pattern, we want to incrementally replace the monolith with microservices one section at a time. Our monolith is deployed inside a virtual private cloud, or VPC, with an elastic load balancer in front of an auto-scaling group of EC2 instances. All of these resources are deployed across multiple availability zones to provide high availability. We also have an API gateway with routes defined for each of the services. Initially, all of those routes are pointing to the monolith. We're going to keep this architecture and add the AWS services we need to run the extracted microservices. First, we'll add an ECS cluster using Windows EC2 for compute. This cluster will run the inventory microservice in Windows containers. As we continue with our Strangler Fig pattern, any services that are .NET Framework only can also run in this cluster. We'll include a load balancer to distribute traffic among the containers. ECS makes this really easy to set up. Finally, we'll update the API gateway to send the inventory route to the microservice. This way, we maintain API compatibility. The API clients don't need to update their code to start using the microservice. Next, we'll add an ECS cluster for our Linux containers. In this case, it's the invoicing service, which is running in Fargate. Just as with the inventory service, we'll add a load balancer to distribute traffic among the containers. Then update the API gateway's invoicing route to point to the microservices instead of the monolith. Finally, we'll add the account microservice to the architecture. This microservice is using Lambda, so we don't have any infrastructure to manage. We will update the API gateway to point to the account microservice instead of the monolith. Now we can see the Strangler Fig pattern really starting to emerge. We have 3 new modern microservices that have each replaced a portion of the monolith without having to make any changes to the monolith itself. Now I'll demonstrate a number of the practices and services that we've covered so far. Let's start our demo with the invoicing microservice. As a reminder, this is the microservice we ported to .NET Core. So we're going to run this microservice in a Linux container to save on licensing costs. And we'll run that Linux container in Fargate because the service has a variable traffic load. I'm here on my Windows desktop, but in order to build a Linux container image, I need to be on a Linux machine. So I have an EC2 instance running Linux and Docker that I've connected to over SSH. This will be the build machine for the Linux image. I've uploaded the code for the invoicing microservice onto this instance, so now we can build and push the image. First, we'll build the image and tag it with the name of the microservice. The Docker build process just compiled the .NET Core code and packaged it inside a container image. This is the exact same code from my Windows desktop. Again, because .NET Core is cross-platform, the same code compiles on both Windows and Linux. Now we need to push this Docker image up to AWS so that AWS services can use it. I've already created an Elastic Container repository for this image. So now we'll log in to that repository and push the image up to AWS. The commands to do this are displayed in the AWS console. Now the invoicing image has been uploaded to its repository. The next step is to create an ECS task to describe the resources that the container needs. Let's go back to our Windows desktop to do that. We can define our task parameters in a JSON file. This is helpful in a number of ways. One of them is that we can put our task definition under version control, so we can track revisions over time. Using a JSON file also makes it easier to use the AWS CLI to deploy the task. So let's open up our task definition JSON. The family defines a name for the task. Each task can have one or more containers. This task only has one. It's defined in the container definition section. We're using the image from our Elastic Container repository for the invoicing microservice. So when this task is created, it will get the image that we just pushed up and use that image to create a container. We're indicating that this task requires a certain amount of CPU and memory. This helps Fargate allocate the necessary resources. For EC2, this will help the orchestrator figure out how to most efficiently deploy containers onto EC2 instances. Now that we have our task definition, let's go to PowerShell and use the AWS CLI to register this task. I'm going to use the PowerShell that's inside Visual Studio itself. The output of this command is a JSON block that describes the task definition. Now that we have a task, we need to create a service in ECS to run that task on an ongoing basis. Again, we can use the AWS CLI to create that service based on a JSON specification. Let's pull up that service definition JSON now. We can see that the service is based around the task definition that we just created. We're launching it in Fargate onto an ECS cluster that I've already created. The desired count of tasks is 3. So the orchestrator will try to make sure there are always 3 identical tasks running as part of this service. Those 3 tasks will be deployed across 3 private subnets, which means the containers won't have direct access to the internet. The tasks are also behind a load balancer, which I've already created. That load balancer is also internal to the virtual private cloud. This means that none of these tasks can be directly accessed from the internet. This is helpful from a security perspective. Because ECS integrates with Elastic Load Balancing, the ECS orchestrator will automatically register the containers into the load balancer's target group. This configuration looks good, so let's deploy this service using the AWS CLI. Now let's pull up the ECS cluster in the AWS console. We see that we now have a service and our tasks are in the process of deployment. If we go to the load balancer target group, we'll see that the load balancer is in the process of checking the health of each container. Once they pass their health check, they'll be added as active targets for the load balancer. This may take a few seconds to a minute or two, depending on the health check, so let's fast forward until everything's up and running. The tasks have all spun up and have been registered with our load balancer. Let's run a smoke test to make sure the containers are working. We can't connect to this microservice over the internet because the tasks are in private subnets and the load balancer is internal only. So, to test the microservice, we'll go back to our Linux EC2 instance, which is inside the same VPC as the ECS cluster. Because we're now inside the VPC, we can connect to the load balancer using its DNS name. If everything is working, we should see some JSON output from the invoicing API. Okay, great. There's that JSON output from the invoicing API. This means the containers are doing what we expect. They're running the invoicing microservice. Now let's deploy the inventory microservice. Remember, the inventory microservice was not able to be converted to .NET Core, so it's still running on .NET Framework. This means the inventory microservice will need to run on a Windows container, not a Linux container. Let's use apt2 container to package this microservice. To do this, we'll switch over to our Windows Server EC2 instance. This is a development server running the inventory microservice as the default website in IIS. This is the microservice that we want to package using apt2 container. To run apt2 container, we'll start with a PowerShell window, since apt2 container is a command line tool. I've already set up and initialized apt2 container on this instance as per the documentation, so we can get started by running apt2 container inventory. The output of this command is all of the running ASP.NET applications on this server. In this case, it's just the default website, which is what we'd expect. Now, we'll copy the name of the IIS root application and use that to run apt2 container analyze. This may take a few minutes to run, so we'll fast forward until it completes. The analyze step has now completed. The output of this step is a JSON file. Let's take a look at that file. You can see the JSON file contains the image that the container will be based on. In this case, it's Windows Server Core 2019, which makes sense because this is a Windows Server 2019 instance. Now we do want to update the base image to use the .NET Framework version 4.8 instead of version 4.7.2. So we'll update the base image to ASP.NET 4.8. This is using the official Microsoft image, which you can find on Docker Hub. The other thing I want to change here is the repository name. A2C has generated a default repository name based on the IIS application name. But this name isn't very descriptive, and I've already created an ECR repository for this image. So we'll change the image repository name to the name of the ECR repository. Everything else in this JSON file looks good, so we can save and close it. Now let's actually containerize the application by running apt2 container containerize. This command may also take a few minutes, so we'll fast forward until it finishes. The containerize command has finished. Let's look at the outputs. First, we'll run Docker images to make sure that the image has been built. Okay, you can see at the top of the list is our AFDS inventory microservice image. Great. Now let's test our container before we push it up to the repository. We'll run the container on the build machine. Once the container is running, we can test it by sending a request to the health check endpoint. Healthy is what we want to see, so this test passes. Now we can stop and remove our test container. Now we know that the container works. so we can use apt2container to generate deployment artifacts. The deployment artifact command has succeeded. This command creates a CloudFormation template that will deploy the container. These deployment artifacts are great if you're starting from scratch. But in this case, I've already created the AWS infrastructure to run this microservice. So I won't use the generated deployment artifacts. Let's just push the image up to its ECR repository, and then we can use a workflow that's a lot like what we did for the invoicing microservice. Just like we pushed the invoicing image up from the Linux instance, we'll push the inventory image up from this Windows instance. Again, the commands to do this are available in the AWS console. We've now pushed the Docker image up to AWS. Now let's go back to our Windows desktop and set up an ECS task and service. Like the invoicing microservice, we'll define the task parameters in JSON. The parameters here have changed a little bit to be compatible with Windows containers. We've also changed our compatibilities to indicate that this task can only run on EC2, not on Fargate, because Fargate doesn't support Windows containers. Now let's switch over to our service definition. The desired count is still 3, so the orchestrator will run 3 tasks across our EC2 cluster. The EC2 instances that make up the compute layer are configured to span the same 3 private subnets as the invoicing microservice. Just like the invoicing service, we're integrating this with a load balancer. I've already created the load balancer and its target group. So let's go back to PowerShell and create the task and then the service. Now let's go to the AWS console and double check the deployment. You can see that our service is starting up and it's placing tasks on EC2 instances in our cluster. If we go to the load balancer, you can see that the service is registering the containers as targets with the load balancer. Now, just like with the invoicing microservice, we can't reach these containers from the internet. So let's go back to our Linux machine inside the VPC and run a smoke test against the inventory load balancer. Now we have our inventory microservice running in Windows containers on EC2. The last microservice we want to deploy is the account microservice. We're using Lambda for this microservice. The account service has 4 CRUD operations: create, read, update, and delete. We've converted each one of those operations into its own Lambda function. Here in Visual Studio, we've included each of these functions in a project under the microservice solution. We've published each microservice to Lambda using the AWS Toolkit for Visual Studio. Just right-click on the project, click Publish to AWS Lambda, then click Upload. Once the publish has completed, let's switch over to the AWS console, where we can see all 4 Lambda functions. Now we have all of the parts we need to start implementing the Strangler Fig pattern. We've defined an API gateway for the OneVision platform. If we go into the integrations for the API gateway, we can see that it's only integrating with the monolith right now. This means the monolith will handle every API request. Unlike the monolith and the microservices, the API gateway is accessible over the internet, so we can test it in PowerShell on our Windows desktop. So this is the invoicing route, and even though we have our new invoicing microservice, requests to the invoicing API are still being handled by the monolith. We want to change the invoicing API so that it's handled by the microservice and not the monolith. To do that, we'll go to the API Gateway Integrations in the AWS console. Here is the root API route, which is pointing to a load balancer that sits in front of the monolith. This is a catch-all route, so everything flows through it. You can see that we've defined routes for invoicing, inventory, and account, but because those routes aren't integrated with anything, the API gateway falls back to the catch-all route that points to the monolith. Now let's go to the invoicing route and set it up to point to the microservice. I've already created an API gateway integration for the invoicing microservice. This is like a pointer to the invoicing microservice load balancer. Now we need to link that load balancer to the invoicing route. So we select the integration with the invoicing load balancer and click Attach Integration. Now if we go back to our PowerShell and execute the invoicing API again, let's see what happens. You can see that the source field in the JSON has changed, indicating that this API request is now being handled by the microservice. Now let's switch the inventory route to be handled by the inventory microservice. First, let's double check that the inventory route is still being handled by the monolith. As long as we're already in PowerShell, let's update the inventory route using the AWS CLI. Now let's check the inventory route again and make sure it's being handled by the microservice. Again, you can see the source field has changed in the JSON, so we know that the API request, the same URL, is now being handled by the microservice instead of the monolith. To update the account service, we'll use a different kind of API gateway integration that points to a Lambda function. Each of our Lambda function handles one HTTP verb: get for read operations, post for create, put for update, and delete for delete. I'll set up the integrations for each verb to its corresponding Lambda function. Now that I've set up each HTTP verb under the account route to integrate with its corresponding Lambda function, let's test the API in PowerShell. This test shows that the account route is being handled by the Lambda function. Our Strangler Fig pattern is starting to come together. We've been able to extract microservices from the monolith without changing the monolith code. We've updated one of those microservices to .NET Core and deployed it on Linux containers with Fargate. We've kept another microservice on the .NET Framework and deployed it on Windows containers on EC2 using apt2 container. And we've converted a third microservice to use AWS Lambda, so it's fully serverless with no infrastructure to manage. Finally, we switched the public API to point to the new microservices, so all of our end users are seamlessly connected to the new architecture. Now we have all of the benefits of a modernized architecture for these microservices. This concludes our demo of serverless and container best practices for modernizing .NET applications. As a reminder, this video is one part of an entire series covering best practices for modernizing .NET applications on AWS. The next video in the series covers choosing databases for your microservices, using AWS's suite of purpose-built databases. Thank you for watching this video, and good luck on your modernization journey.